Hey everybody, welcome back. It's Ripley back again. Now, in the last section, we talked about the limit. Remember, we took the limit as t approached a of r of t. Remember, r of t is a vector valued function. It's you give me a t, I hand you out, or excuse me, I hand you back a vector. As soon as we went there, I would bet that a lot of you started thinking, wait a second, if we're taking limits, chances are we're probably going to take derivatives. Well, let's just dummy up for a sec. Let's just take r prime of t as we know it. All right. The formal definition of derivatives says that the limit of r prime, or excuse me, the r prime of t can be written as the limit as h goes to 0. Just nothing is changing, right? We're going to have to define this little h thing here in just a sec, but you'll see this is going to be r of t plus h minus r of t all over h. Right? So let's try and figure out exactly what this derivative is. Right? That's just a definition. I didn't change anything. The definition of a derivative shouldn't change with the functions. This should be the definition of derivatives for all things. Now, let's think about this. So I've got a function. Sometimes I get a little crazy with how I label these. You're going to have to forgive me. This is going to be at, wait, how do I want to do this? I want to do, yeah, let's make this x. Let's make this y. Let's make this z. I'm going to try and be consistent with that. All right, so what we have is we've got a curve passing through space, right? So here comes my curve through space, okay? Okay, and I'm going to try and figure out, by the way, I think I neglected to mention this in the last video. This is referred to as C. What I've got drawn here, let me get rid of, well, it doesn't really matter. C is equal to the set of all points. It's the set of all points x, y, and z. This is an ordered triplet, all right, such that the points are on the curve. You should be in R, by the way. They're all in R, are on the curve. All right. So I just put that on here because your esteemed author puts them on there. So I want to make sure we get it. Now, what I want to do is I want to try and figure out the derivative. Let's make it obnoxious. At this point, which I'm just going to call P. All right. So remember from way back, what we have is we have a value, or excuse me, a vector. All right, and that vector is going to be, it's going to start there, and it's going to be r of t at this point P. So the question is, what is r of t plus h? Well, time changes, right? So let's simplify this quite a bit. I'm going to call this Q, and I'm going to call this guy r of t plus h. So what this is this minute little change in t that moves me farther down the curve. That's all that it is. Just like, if you remember how we did derivatives before? Here was, this is x, this is h, this is x plus h. So what we did is we moved over h, whoop, this was x f of x, and this was x plus h f of x plus h, right? But we don't have the benefit of describing this in a planar manner, or excuse me, of describing this change in a planar manner. So we just say, all right, let's take vectors. We like vectors, right? We're starting at P, we're finishing at Q, and then what are we doing? Just like here, remember the fishing expedition? I'm sure you guys got tired of hearing me talk about that, right? Got my point here, I drew a secant line, and then I slowly but surely took the limit. Remember, the limit gave us the ability to do that until I ended up with the tangent line. All right, so what we want is we want to be able to do exactly the same thing by shrinking h to 0. We're going to draw this back here, and what we'll end up with is a change between r of t plus h and r of t. And what that's going to do is, very much like here, is it's going to spit out a derivative. A quote-unquote tangent vector, all right? That's what it's going to do. It's going to spit out a tangent vector. Now you may say, well, wait a second, Ripley, how do we get this tangent vector by dragging these two other vectors back? Well, how did we get a line by dragging these two horizontal lines back? Don't let the direction of these vectors confuse you, just like you shouldn't have let the direction of these vertical lines confuse you into giving this. Again, if push meets shove and you're confused, just look at the notation and look at the process. We're doing exactly the same thing. Now, there is one thing that we need to talk about. It's called the unit tangent vector. The unit tangent vector is really, really important because, as you note, this vector could have a whole assorted and sundry different lengths, right? We've got all these crazy, like this vector could represent the behavior of this curve. Let's change colors. This obnoxious green, vomit green vector could as well. So as mathematicians, what we want to do is just say, no, 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 no. We don't want any ambiguity in this. We want to be unequivocal. So what we're going to talk about, we're going to stick to one vector, which is going to represent the tangential behavior, just like this line was tangential to the curve. This vector is tangential to the space curve, all right? And we're going to call it the unit tangent vector and make our lives much easier. Now, you can kind of think about how you do that, right? The unit tangent vector has a capital T. This guy's bold. I really need to figure out how to do that, right? Well, how would you do that? Well, how do I make any vector into a unit vector? I divide by its magnitude. So this is going to be r primed of t divided by the magnitude of r primed of t. Now, we're not going to get into this because I don't want this video to be 9 hours long, but if you think about it, now remember, these are vectors, and I need t values to make these vectors hum. If I want r of t, if I've got r of t and I want it to spit out a vector, I got to throw a t value. And remember back in the other video, if r of t equals sine t, cos t, and then t, just for giggles, right? Well, let's play a little bit. If I do r primed of t, now, what's your intuition before I start taking derivatives? If we go back a bit, just a couple. Oh, that was fun, wasn't it? The toroidal spiral. If I go back a bit, what was the rule on limits? Well, whoops, I went too far back. Sorry. What was it? It was this guy right here. The limit of the vector is the vector of the limits. So I can stuff the limits inside. Well, where did derivatives come from? Limits. So what should be true of derivatives of r primed of t? Well, shouldn't it just be f primed of t, g primed of t, and h primed of t? And I promise I'm not going to do this much longer because hopefully you'll get it, but this is equal to f primed of t I plus g primed of t j plus h primed of t k. All right, done. I promise, I'm done. And that was all just like it was back in regular calculus. It's all, the precedent that we use is the limit. It's all predicated on the limit. Since the limit gets stuffed in the vector, so too does the derivative. Okay? So in this case, right here, I've got r primed of t is equal to cos t, negative sine of t, and t. Whoops. And t. Now, I don't know about you guys. It kind of sounds like fun. Oops, not t, but 1. All right. So if I want to do r primed of pi halves, well, I know what it's going to spit out is 0, negative 1, and 1. Now, be careful. Let's look at this thing for just a sec. I want to actually graph this on our grapher. Now, I already put it in, and I'm going to show you what it looks like. Here it is. So let's drop this guy down really quickly. So I've got sine t, cos t, and t, just like I said. I went from 0 to pi, just because I figured that'd be fun. Now look at that. Isn't that thing beautiful? Check it out. I love math. Math rocks. Now, let's see if we can figure out why this did what it did. Just for a second. Let's take a minute, all right? Because being able to visualize these things can be really, really tricky. I mean, some of them, you're not even going to have a shot at it. But let's look. All right. When we start at 0, we know that x is 0. We know that y is 1. So if we look at this, here's my y sitting right here, and we know that t is 0. So this is my initial starting point when t equals 0. And then what happens? Well, this thing curves up. Well, where does it curve up to? Well, we know the behavior of sine, so we know that x is increasing up x is increasing up to 1 and then down to 0. We know that cos is decreasing down to 1 and then down to negative, or excuse me, down to 0 and then down to negative 1. And t is just chugging along from 0 to pi, which is pretty cool. So let's see, where did I forget, where did I take the derivative at? I took the derivative at pi halves, right, which is halfway through. So let me drop this again. Halfway through this curve, this c, this set of c's, I want to figure out what the vector looks like, right? So what did I do? I come back here. I'm going to make myself, excuse me, whoops, what is going on here, Ripley? I'm sorry, you guys. I'm acting like a crazy person. Well, what are we going to do? We're going to take this vector right here, and I'm going to take that thing and I'm going to divide it by the length of the vector. Does that make sense? You with me? So I know that t of t, that is the unit tangent vector, is going to look like, I'll take 0, -1, and 1, and I'm going to divide it by the square root of 0 squared plus -1 squared plus 1, whoops, plus 1 squared. Ignore that, please. And this thing ends up being, what is it? Well, remember, this is a scalar, so it's just going to pop into the vector, right? I can multiply or divide scalars into vectors, so this is going to be 0. What is that? -1 over root 2 and 1 over root 2. And if we had to check it, we could square this, add it to this square, add it to this square, and I better get 1 to make sure that it's a unit vector. Another way to write that sucker is -1 over root 2. I'm going to bug you guys so badly with this. Plus 1 over root 2. Okay. You can stick in the 0i as well if you'd like, as well as you'd like. Now, this is kind of key. And then I'll be done talking about derivatives and unit tangent vectors. Remember, if I were to graph this really quickly, if this is x, this is y, and this is z, what would this look like? Well, it would come out this way. Let's get this. I've got -1 over root, so let's see, we go that way, z is positive. So it would actually pop up here, right? That's how it would be drawn. And you may say, whoa, 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 but Ripley, that looks nothing like what it should. This is nowhere near the origin. Well, we don't panic, do we? We remember that vectors are mobile. I can move them wherever I want. I can stick them wherever I'd like. So that gives us that ability to move that thing where we need to. This doesn't look exactly like this because of the way in which their vectors are set up. I would have to make it look like mine, because you may say, well, wait, this is going the wrong direction, which technically it is, but not if you look at how their axes are set up. So I apologize for that. Okay, let's really quickly go over the differentiation rules for vector functions or vector value functions. But the thing to remember is we're just doing an extension from the plane into space, okay? That's key. All right, so you'll start seeing some very predictable patterns popping up in these differentiation rules. So first things first, let's suppose that u, let's make that v, and u are diffable. Differentiability means exactly the same thing here as anywhere else. Okay, so diffable functions, they're vector functions. Make sure we get that, vector functions. And excuse me, let C be a scalar. C is a scalar, and f of x is a real valued function. Valued function of a real variable, real valued, sorry guys, function of a real variable. Okay? All right, easy peasy. So you ready? We'll just write these down really, really quickly. So the derivative of a sum, predictably, u of t plus v of t equals the sum of the derivatives, right? Nothing to be afraid of. U of t plus u of t of v of t, just like you would expect, right? Nothing to it. The derivative, yeah, you can probably see where this is going. The derivative of a constant times u of t, and we'll put this whole thing in brackets like that, is equal to the constant times u prime of t. Easy peasy. Part 3, if I do the derivative of a function f of t. Now, I know that I changed the variable, but remember that variable can basically be anything. I should have just written f instead of f of x to decrease, to mitigate any confusion. But look at this guy. Just like you would expect, it's a product. So f prime of t, u prime of t. Now, again, these should be bolded. Maybe I should start underlining them. No, that can get confusing. Whoops, not times u prime of t. Somebody shoot me. Don't shoot me. Just kidding. God. Plus f of t times u prime of t. Or, now here's where it starts to get interesting. I love this. This is d over dt of u of t, vector value function, dot, right? We're talking about a dot product here, not multiplication. However, we know the behaviors of dot products with vectors is very akin to the behaviors of products, as that will play out predictably here. Plus u of t v prime of t, yay, it works exactly the same way. All right, that's pretty cool. All right, then last, well, not last but not least, but watch what happens here. How about u of t? Oh, by the way, let me put that in parentheses, u of t cross v of t. Now, what do you think is going to happen with the cross product? Well, it's pretty cool. It's just u prime of t cross v of t. So it behaves the same way as the product, which is surprising. Now, we're not going to prove this per se, but we will discuss it. This is u of t cross v prime of t. I think that one's awesome. That's my favorite. And then last but not least, now this is going to have a little chain rule feel to it. What would you expect this to be? So this is going to be u of f of t. Well, now think about what's really happening here. I've got a vector valued function, right? U of t, right? This guy's just going to be, you know, t squared sine of t squared, right? Well, all we're doing is a composition of functions. Like t squared is a composition with sine of t, right, or sine of x. T squared in and of itself here could be a composition with just t. So just like we would predictably say, oh, that's a chain rule situation, only this is a function and that's a vector valued function, we get exactly the same type of behavior. We end up with u primed of f of t times f primed of t, right? Works just like chain rule. We've done this before, and we get to use it over and over and over again. All right, so that's the rules for differentiation of vector valued functions. All right, that's enough about derivatives. Well, if we talked about derivatives, you can probably figure out what we're going to talk about next. Let's talk about integrals, right? So I know if I'm going to take the integral, I'm going to take a definite integral from a to b of r of t. Remember, r is just a vector valued function, dt. That's this guy right here. I know this is going to be the limit, just like before, as n goes to infinity, of the sum as I goes from 1 to n of r. Let's see. Now, I'm not going to use that asterisk thing that your textbook does, right? And then this is just going to be delta t. All right? I'm just using the formal definition of integral. Nothing new, nothing crazy. But remember, this is a sum, right? We've got this sum in here. We're adding up a bunch of terms, and this is a limit. Remember how our limit worked before? We got limit of the sum is the sum of the limit. So I can stuff that limit. I mean, think about this. Think of this as a vector. Okay? So we've got a sum of vectors, but I know the limit of the sum is the sum of the limit. So I can stuff the limit in here, and we just figured out that the limit of a vector is the vector of the limits in last section. So that becomes really simple. I can simply rewrite this as the integral. Now, I'll do it like this. This is going to be the integral from a to b of f of t dt, the integral from a to b of g of t dt, and this is going to be the integral from a to b of h of t dt. And that all stems from the fact that the limit of a vector is the vector of a limit. It's really simple. Now, indefinite integrals, you may say, well, indefinite integrals get really, really tricky because we are going to have to be able to figure out it doesn't make any sense to have a bunch of plus c's here, because in 4 space you're not getting a family of curves, you're getting a family of vectors in all directions, right? If I have a plus, let's move over, if I end up with the indefinite integral of f of t dt, I think I said indefinite interval before, but if I said definite, just ignore me, dt. If I do this, I get no information. Can you see why? If this guy has a plus C1, and this guy has a plus C2, and this guy has a plus C3, I have an uncountably infinite number of vectors that go in all 3 directions. So you have to do this with definite integrals. So I'm not going to bore you with an example of how to take integrals. We did a million of them last year. We'll do those in class. I just wanted to make sure that you understand the beauty of, once we committed to that fact that the limit of a vector is the vector of the limits, like, we're done. Look at how easy this is. The extension into 3 space and 4 space with the parameter is really, really simple. All right, thanks for listening.